So what I tried to do was I tried to leave that time open so I could fill in as many holes in my lecture notes as possible, because I might not have written it down, but I remembered it, as long as it was right after class. If I waited an hour or two after class, you know, your memory goes exponential, I think. You lose it very fast. And so even if it was like 3 hours later, then I would have forgotten so much. And so right after class, I would have filled in all the holes. And then, you know, my goal was by the next test, I understood everything that was presented in lecture. And so you would try to do it like right after class. And so if you do that kind of stuff, then maybe yesterday's quiz might have been easy points, perhaps, you know. Because you might not have written it down in your notes, but you know, if you had it like kind of in your memory, and then maybe you could have done it, or if it was still uncertain about it, then you could have asked, you know, at the beginning of class. But for CO2 and water, what kind of reaction is this? Did we do this reaction in class the other day? Yeah. What kind of reaction is this?
Acid base.
Well, it's not your regular acid base. Your regular acid base is a Bronsted acid base.
Lewis acid?
Yeah, it's a Lewis acid base. And whenever you show a Lewis acid base, you have to think about the Lewis base. What does the Lewis base want to do? Lewis bases want to... Lewis bases are electron. You see, this is this kind of stuff. Maybe it wasn't clear during class, but like right after class, if you kind of read through your notes and then just fill in the holes, you might get it. Lewis bases, or you know what I used to do also is read my notes every day. I read my notes every day so that I'd have everything memorized.
That's the one where we had to prove if it yields carbonic acid.
You just had to show how it could yield, right? Carbonic acid. I think this is my water. So Lewis bases are electron pair donors, and that should be easy points right there. Lewis base, electron pair donor. So what we do is we had two choices. Water could be the base, and CO2 could be the acid, or CO2 could be the base and water could be the acid. Well, those were the two possibilities, the only two possibilities. But I told you that CO2 being the base and water being the acid was a dead end. You remember that? And so if you could have tried it, like if you forgot it was a dead end, you could have tried it and it would never have yielded carbonic acid. You know, but if we made CO2 the acid and water the base, then yes, this could yield carbonic acid because, and so we just show it like this, you know, we'll have too many electrons. Carbon already has an octet, so it's got to kick some of those electrons out. And so we show it step by step. And the important thing is you have to show what's happening with electron pairs in Lewis acid-base reactions. This is called a mechanism. And so a lot of people were missing these arrows. These arrows are very important because you got to show what's happening mechanistically. And so when I say show Lewis acid base, this is how you show Lewis acid base reactions. You got to draw these arrows showing the base. I've said this a number of times. For Lewis acid base, it's always the base attacks the acid. The base attack. But you know, I said it was a little bit tricky for calcium oxide because the base was kind of locked in a lattice. So hopefully the water came by and the base was able to attack the acid once the water collided with it. And then we end up with something like this. And then I mentioned that, well, whenever you have non-zero formal charges, you always have to write them. And so all the formal charges are zero here, but these are non-zero. So for example, we had a positive formal charge on that oxygen, a negative formal charge on this oxygen. And so if we have non-zero formal charges, we need to write those in there. And then there's free rotation about single bonds. So this thing's rotating, you know, this water that kind of got stuck on here. And so this hydrogen can rotate close to this oxygen. Well, this oxygen is quite basic. This is like hydroxide, and this is like hydronium. I wrote those down, I think. I wrote hydronium to show that this is analogous to hydronium. And I don't think I wrote hydroxide, but can you see that this is analogous to hydroxide? And so we have hydroxide and hydronium, but this is strong acid, strong base. And so, you know, we just let this rotate. And so I'll just let it rotate. It's the same structure. But, you know, I could have drawn it differently. I could have already had it rotated in the correct orientation. You know. And so then I had this. What did I call this? Does anybody recall what I called this? So I had this happen. This oxygen lone pair vibrates, you know, there's vibrations, and it gets pushed into that hydrogen, which kicks those electrons out. You know, this is very favorable because this is, you know, quite basic here, and this is quite acidic here. You know, I don't know if I said this, but compare the acidity of this hydrogen versus this hydrogen. There's a world of difference. The world of difference is the electronegativity of oxygen is 3.5. But what happens if the oxygen has a positive charge? Is electronegativity the same, 3.5, higher than 3.5, or lower than 3.5? What happens if you put a positive charge on there? Does it become more electronegative, less electronegative, or does electronegativity stay the same? Electronegativity is the ability to attract electrons. Electrons are negatively charged. So would a positive species have greater ability to attract negative charge or reduced ability? Greater. So the electronegativity is higher. And so what that means is this. It means that, you know, the acidity on this hydrogen is due to a delta plus, and water is not that great of an acid. But this is much better of an acid because of the positive charge on that oxygen sucking the electron cloud towards it, which makes this hydrogen much more acidic. This is like hydronium. And we have this. Now, what did I call this? Does anybody recall what I called this? And so, do you see? This is why I had to change the way I studied. You know, this is exactly like everybody else, you know. I don't know what you call that. It's kind of weird. But, well, you know, I told you, did I tell you this yesterday? I went to orientation at UCLA, and they told me, oh, your GPA is going to drop precipitously, you know, basically. Did I tell you that story yesterday? Yeah. And so this is one of the tweaks I made. I made sure I understood everything in lecture, and and then I reviewed it every day, so I had it memorized. So if somebody had this was easy points. You know, this is like free points because this was straight from lecture. And what did we call this? Do you have that written down? Sometimes it's too, you know, okay, I didn't write it down on the board, but that's what happens. I've had lots of lectures where the professor didn't write anything on the board. All the professor did was stand at the podium and start talking. That's it. And so you're there just writing. And so you want to know as much as possible. And so what we called this is, did I talk about the difference between inter and intra yesterday? Maybe not. Or the day before? Mm-hmm.
So when it comes to studying, I noticed when I was at UC Santa Barbara,
mm-hmm.
For economics, we have like a tutor who can help. They'll give us, you know, all this information, old tests and everything.
Oh, that's a great tutor.
Yeah, but
yeah.
But here's the crazy part.
Mm-hmm.
Every time the test would be different. The department would, you know, make
purposely.
Yes.
So you studied all this stuff, and then all of a sudden nothing from that came. Yeah.
So,
you know, that's exactly my experience.
Yeah.
That's exactly my experience and in fact, it's purposely done that way because in all the chem classes, exactly the same. And then the students always complain, hey, you know, what do you do? What's your philosophy on this because you always throw questions that are totally not what we expect.
Yeah, and especially the very last question, nobody basically was able to answer it because it was something we were just so unprepared for.
Yeah. That happens quite a lot. But the thing that helps is if you just get these down, you know, so it's memorized, then you can hopefully have enough tools memorized that you can work out more difficult problems. You know, that's the only thing. A lot of the classes, though, that I found, at least in Chem, a lot of the material was just the stuff presented in lecture. But the problem is did you remember it, you know? I briefly talked, maybe I briefly mentioned this, maybe I didn't, you know? But this is called an intramolecular proton transfer. You know, normally we have an inter, you know, between two. So we have an interaction between the acid and the base. You know, and the base attacks the acid, collects the proton. Those are two separate molecules or two separate species or two separate ions. In this case, it's happening within the same species, the same. And so one part of this is, and this is why we look, you know, this is why I labeled acid site. Do you remember acid site, base site, that kind of stuff? So we can look for these kinds of things. And so we have this intramolecular proton transfer. Most Bronsted acid-base reactions are intermolecular. And then we end up with carbonic acid. Carbonic acid is not that stable, so this can easily reverse. But what happens is it's unstable, but that doesn't mean the whole population will get there. Most of this will stay as CO2 and water. Most of it. But we have a Maxwell-Boltzmann distribution. And so what can happen is, you know, this is kind of an energetic pathway. This is an energetic pathway because is this very stable? No, this is kind of higher energy. And so what can happen is there could be a small population of CO2 and water that have enough energy to climb up this hill to form carbonic acid. And that's the case. Most of it, you know, if I had a bunch of carbonic acid, most of it will fall down the hill. But, you know, there's going to be, because we have a Maxwell-Boltzmann distribution of energies, there's going to be a few that make it up. And that few is going to lead to what we call a steady equilibrium. That is, for every one that decomposes here, then one will come back up. And so we end up with this type of situation. The population is going to be quite small here because it's not that stable. And so in terms of driving force, the driving force is back to the left. But for Lewis, you don't really worry too much about the driving force. For Lewis, it becomes a lot more complicated. Speaking of UCSB, there's a professor. He's actually long since retired, but he was there when I was there. He came up with a HSAB theory for Lewis acid-base reactions. You know what HSAB stands for? HSAB stands for hard, soft, acid-base theory. And so this was very useful in predicting Lewis reactions. So it's very simple. A hard acid likes a hard base. A soft acid likes a soft base. Hard doesn't like soft, or soft doesn't like hard, you know, vice versa. And so this is good, this is not so good. Hard and soft. And so we look. So, for example, potassium ion is soft, whereas iron 3 ion is hard.
So, you know how, like, when I was asking you about how you treat something, like, let's say we're looking at this and we know how to treat it like an acid or anything like that, but what if you're given something and you don't know what it is, like, you don't know how to treat it? like it doesn't like fit that criteria, I guess. If that makes sense.
Like this generic, I mean some
Yeah,
other
so like-
species, yeah. Oh, this is what we do. We use all the tools that are available to us. So what tools do we know? We know how to do formal charge. We know how to do oxidation states. We know how to do delta pluses and delta minuses for polar bonds. We know that kind of stuff. So we can sit there and try to figure it out. Let me just finish something here. Oxide versus sulfide. Which one is harder? Which one's softer?
Oxide harder,
Oxide harder, sulfide.
softer.
Yeah. So we can kind of see what kinds of interactions are favorable based on that. But HSAB, this is beyond the scope, Chem 1A, but you know, there's tools that we can use to try to figure out, you know, driving force for Lewis acid-base reactions and the acid strength and the base strength.
Is the hardness and softness like from the size?
Mm-hmm. From the size, right. It's due to something called polarizability. You know, the electron cloud. How polarizable is the electron cloud? Turns out heavy metals love soft anions, like lead. Lead 2 loves sulfide. It much prefers sulfide over, let's say, oxide. You know, that kind of thing. But Bronsted, oxide's a more powerful base. Lewis, it depends on what you're reacting with. Oxide might be more powerful or sulfide might be more powerful. It depends on the acid. And so it becomes a bit more complicated, but in Bronsted it's simple. Oxide is more powerful because the acid's always the same. Bronsted is a lot easier because the acid's always the same. Did I do the other Lewis acid-base reaction? BH3 or BF3 and NH3? Did I do that one? BF3, you tell me. Okay, we have a new species here. All right, so here, this is Gabe, getting back to Gabe's question. What is that? Is that a Lewis acid? Is that a Lewis base? Or neither? It's definitely not a Bronsted acid because there's no H, and it's not a Bronsted base. It's not a proton acceptor. In terms of Lewis, how would you analyze this? In terms of Lewis, we'd analyze it like this. Here we have a lone pair, and it depends. If the lone pair is shareable, then we'd like to share it. And so it seems shareable because that's a delta minus on fluorine, right? There's going to be a delta minus on fluorine because this is what we call a polar covalent bond, and there's going to be a delta plus on boron. So, in terms of electrical interactions, bases are negative or bases are positive in nature? Negative. And so this could be a base here, and so it could be an electron pair donor. And so, and then the positive is an acid, right? In fact, this could easily accept it. This is one that is very commonly done. So I'm going to have an intramolecular Lewis acid-base reaction. You want me to do it? An intramolecular Lewis acid-base reaction? Yes. I'm going to do it. I'm going to take this lone pair and donate it to the boron, like that kind of thing, in a way. It's not perfect, but if I do that, I end up with this. What's good about this structure? What's good about this structure is now boron has an octet. You see that? Boron has an octet. So boron definitely wants another lone pair, whether it's shared or given to it completely. But what's bad about this?
I think fluorine wants the octet more.
Fluorine still has an octet. Fluorine still has an octet, so isn't this win-win? Well, not really. It's not really win-win because in order for this lone pair to go here, fluorine ends up having to share it. Now, if it shared it evenly, that means one electron goes to boron, the other electron goes to fluorine. And so actually fluorine comes out net loser because look at what happens to the, not the oxidation, what happens to the formal charge? Over here, all the formal charges are 0. This is BF3. Here, the formal charge on fluorine goes from 0 to 1, 2, 3, 4, 5, 6. It's supposed to have,
7.
so the formal charge goes to +1. And then boron's formal charge goes to 1, 2, 3, 4. It's supposed to have 3. It goes to minus. So essentially, fluorine gave him an electron to give to boron. Do you think that's going to happen? No. And the reason is fluorine is quite electronegative. It's not going to happen. And so even though we might have predicted fluorine's going to be a Lewis base and donate a lone pair to boron, it's not happening here. Not happening. Because there's no way if boron and fluorine got in a tug of war, that boron would win. Fluorine wants all the electrons to itself. The lone pairs, who is the lone pair shared with? Nobody. Those lone pairs belong 100% to fluorine. It doesn't have to share them. And so here it's sacrificing one lone pair to make a bonding pair. It's not happening. So this is how you analyze it. You analyze it by looking at this. Okay, so, well, boron trifluoride is not going to be a Lewis base. It's not going to be a Lewis base because fluorine will never want to form more than one bond. Otherwise, its formal charge goes like that and it has to share too many electrons. But this ends up being a powerful Lewis acid. Boron is happy to accept the lone pair. It just has to be from some other molecule or some other species. So in this case, we can react this with ammonia. Ammonia is both a Lewis acid and a Lewis base. Here, nitrogen's delta minus, hydrogen's a delta plus. So what can happen here is this. So this is option A, which turned out to be a dead end. And then we have option 1, like this. So this lone pair attacks the boron here. And in that process, it's going to make this. So now the lone pair has been shared with boron. Now boron has an octet. Before it didn't have an octet. And so this turns out to be a very favorable reaction. But the same thing happens with the formal charge. Boron ends up with a negative formal charge. However, nitrogen ends up with a positive formal charge. Nitrogen's not so happy with the positive formal charge, but it's all right. It's like ammonium in a way. And at least it makes an octet on the boron here. And so this is a favorable reaction. Yeah. So what we do is, for Lewis acid base, you have to analyze the Lewis structures. You have to see, is it possible to donate a lone pair? In this case, it's easy. We don't have to move. We don't have to kick out any electrons. You know, this is a powerful Lewis acid because it has less than an octet. And it can't gain an octet because this doesn't happen here. So Lewis acid-base reactions are a lot more complicated. And therefore, I don't spend that much time on them because it's time-consuming to go through. But that doesn't mean you shouldn't go through it. You know, you should make sure you understand it. The other Lewis acid-base reaction I had on the quiz was calcium oxide in water. You know, the thing is, don't worry if you don't understand it. Don't worry if you don't understand it. That's most of the stuff. You know, I took a lot of classes at UCLA. I didn't understand anything in the lecture. I would have to go home and then try to figure out what the heck was going on in those calculations, or what the heck was going on. And that was just common. The classes are really hard, some of them.
I heard it's because the professors are paid to research, not to teach. That's why.
Well, that's maybe one of the reasons. Another reason is there's too few hours in lecture. They have to skip a lot of stuff. So they skip so much stuff, it's hard to follow it, you know, where you're going. So that's why I had to go home and then figure out, you know, how they got from here to there. And that usually took a lot of time. But it's true, the professors are paid to research. Sure. It's, they have this phrase that they say, publish or perish, you know. If they don't do research, then they're not going to have a job for too long.
So when you were going to UCLA, did they have TAs?
Oh yeah, TAs for every class, except for the really small ones. The smallest class I had at UCLA only had 4 students. No, it's cosmochemistry. There's no TA. Professor did all the work. It was a graduate class. You can take graduate level classes as undergrad. Sometimes the graduate classes are easier than the undergrad classes. So the thing for something like this, and, or actually the previous one and this one, calcium oxide and water, the first step is don't worry about understanding it. Just copy it down. Can you copy it down and memorize it? Or you can copy it down and memorize it by going through it every day, you know, then it'll click eventually. You know, things will fall into place, and then you understand it. You know, the goal is to make sure it clicks before the exam. But if something doesn't make sense and you don't even bother, you know, it's too confusing, you don't bother to write anything down, then you know, you have nothing to study. And so if a question like that comes up on the test, do you even have it in your notes? The worst exams I had were as a graduate student. When I was at UCSB as a graduate student, I had quantum. I was taking advanced quantum mechanics. And it was a take-home exam. And we had 1 week to finish it. And everybody in the class, all they did was quantum. They couldn't study for any of their other classes because the exam took up, it was like a time, it was like a black hole of time. It was like, it just gobbled and gobbled and gobbled up time. And he still was far from finished. You know, it was just the worst experience I had because, you know, it really hurt my other courses because the exam was just too hard. But everybody was in the same boat. That's why I have a real, you know, trauma when it comes to take-home tests. I hate them, yeah. Okay.
Well, that's how like Caltech works.
Yeah, right. And other places, I guess Caltech, MIT, and those places, they don't care. You could have the take-home exam. You know, you aren't going to be able to Google the answer, unfortunately, though. All right, so that was the quiz. The calcium oxide, did that make sense too? I saw a lot of people, you know, when you write, there are two types of Lewis structures. There are Lewis structures for ionic compounds and Lewis structures for molecular compounds, and you don't mix them together. So if you're dealing with an ionic compound, the Lewis structure for ionic compounds is like this. We don't write covalent bonds between ions. You know, this is why I said, you know, the second structure, the calcium sulfate structure, I said was weird. It was weird because they were making covalent bonds between the calcium and the sulfate. Do you recall that sphere? And I said, no, that's not right. That's not how it's normally done. All we show is the ionic bond like this, so don't draw a line. Some people drew double bonds here. We don't want double bonds here. You know, what it is you have a positive sphere and a negative sphere. And so you just put these spheres together. And so I built out the lattice a little bit, like this. Now all the ions are locked in the lattice. This is like the sodium chloride kind of lattice here. And normally, this is what I mentioned, normally the base attacks the acid, but this base can't attack. This is why, even though oxide's a strong base, calcium oxide's a weak base. Why is it a weak base? Because the oxide's locked in the lattice, right? It's stuck in the solid lattice. So that means it can't go out and react with everything it wants to react with. It has to wait. It has to wait for water to come by. And when water comes by, then it can attack. Well, it can't even go out and grab the water. It has to wait until the water essentially goes in its mouth, and then it can attack, right? And so we'll just have water come here. Now water is amphoteric. And so rather than using the base end of water, the base end of the water was oxygen. We're going to use the acid end of the water. And so we have to wait until this water collides with the oxide, and then boom, the oxide's going to pluck that hydrogen off. This is kind of like Bronsted anyway here. And then it's going to leave behind those protons. And what do we form? We form calcium and then one hydroxide here. So this oxide is going to be converted to a hydroxide, an HO minus. And then this water is going to be converted into hydroxide. So it forms two hydroxides. You know, some people wrote one hydroxide, but it's going to form two hydroxides. One. And you got to show the arrows, you know. And so, calcium hydroxide turns out to be soluble, so this whole lattice will break apart once the hydroxides form here. And so this will start breaking apart. Well, that kind of makes sense because an oxide's a 2 minus, hydroxide's only a 1 minus. So the ionic bond here is going to be like half the strength of the ionic bond here. You know, because it's +2 minus 1 versus +2 minus 2. And then the water gets converted into a hydroxide up here. Now, normally for non-zero formal charges, we write them. For hydroxide, you don't need to. Most people know where the negative formal charge is. And then we write the net charge, that is the sum of the formal charges outside. So hydrogen is 0, oxygen is -1, so 0 minus 1 makes -1, etc. And then the rest of the lattice can be attacked. So this was the other reaction. This one we can do a driving force because oxide versus hydroxide, which one's a more powerful base? Oxide is more powerful than hydroxide. So the single biggest thing that I did that really helped my grades was doing just this. I made sure I understood everything in lecture before the test. Usually the professors at all the schools do their exams based on their lecture. And that's very common. They might give practice exams out, but they certainly aren't going to give the same kind of questions on the real exam as the practice exam. That's something I felt.
So if you
And
have
so,
an instructor who will tell you straight up that I've had this, they will be like, they make sure not to include any examples in lecture in the exam.
yes.
So like, what would be the best way to study in that sense?
Well, I still think just doing everything. This is why, remember I said that one of the other things I found quite successful was doing every single homework problem? That's why. You do every single homework problem, then you see all the variations of the concepts. You know, they try to do, in the homework, when you look at all the homework problems, they try to give you a broad spectrum of problems in the homework set. And so that's also a very successful way of doing it. The top student, I told you, I might have told you this, I never thought of doing all the homework problems until I was taking Chem. And when I was taking Chem, then I saw the top student, you know, he got the high grade, and he was sitting right next to me. So I started talking to him about it and finding out how he prepared for the test. He's the one who told me he did all the problems. And then I asked him, how? It's impossible. I spend 2 hours on one problem, I still don't have the answer.
Yeah.
Yeah. And then, oh, it's easy. You have the complete solutions manual. You don't actually do it, but you see it. If you see the entire spectrum, then you know there's nothing mysterious, nothing hidden, right?
So like.
Right. It's the fear is the fear of the unknown. But if you already know pretty much everything, then there's nothing to fear. But still, they can throw something else unknown. And of course they can throw something else unknown. So I did one other step. Do you want to know what my additional step was? My additional step was I'd go to the bookstore and I'd look at the next class above. The next class above, and then I'd start looking at all the problems there. And then see if I see something new. And so I'd get the more advanced text, and then I'd check that out. But you know, I was just at UCLA last week in the bookstore, and you can't do that anymore. I went to the bookstore because I was curious, what are since I was already there, I was curious what textbook they're using for Chem 1A over there now. Because I wanted to see the level. And I couldn't do it because now it's all online order, and then you pick it up in a bag. And so yeah, can't do that anymore. That was so useful because I just go to the bookstore and just start flipping through books and seeing if I can figure it out.
Instructors who would just write their own problem as well. Right?
Yeah, right. You write your own problem, right? It's not that you're going to be 100% successful all the time, but you're going to be pretty good. You're going to be pretty good.
Like the way I think about it, at least I think you and my high school professor grade in terms of, say if we're doing like a conversion, how many steps you got along.
Yeah, how many steps?
Like how much you got right before you screwed up, pretty much.
Yeah. I've had classes where if it's wrong, there's 0 partial credit. I've had classes like that. I didn't like it. And then I've had, different experiences. But the thing that I liked was if there was a problem similar to the homework or similar to any problem done in lecture, then I thought easy points, guaranteed, 100%. You know, because I would have made an effort to memorize all that. But the thing is, okay, what if there's a problem that's not like that? Well, if there's a problem not like that, then at least you have all the basic tools down that you can try to figure out. You know, use those tools to figure out more complex problems. And usually the more complex problems are just an extra step or two. Nothing like, nothing impossible.
I'm just kidding.
Anything else about to pass out? That's not nice.
All right, let's.
Monster.
Well, that's what I found useful, but you have to find your own thing that works best.
How much sleep did you get at UCLA or grad school, Professor?
When I changed, I'll tell you, when before I started doing this, before finals week, I'd get 0 sleep because it's too much stuff to cram. So I just wouldn't sleep, and then my stress levels were high. After I had everything memorized, then when it came to finals week, I had everything memorized, so it was very relaxing. I just flipped through the notes again, and so it was a lot easier. And so then I got reasonable sleep, but you know, you don't get much sleep as a student, regardless. You know, it's just too many things to do. So, you know, the UCSB, they have a 24-hour library, you know. Yeah, you know the.
Yeah, that was so cool.
Everybody was there. And then, same thing at UCLA, they have 24-hour. So
I
you
did
could.
that during finals week. I would just like
Yeah.
basically sleep in the library.
Yeah, that's what. And so it did the same thing.
Convenient. I wish that's the thing I don't like about coming here on is like the library closes so early here.
Yeah.
It closed like at 7.
Oh, that's too early. That's way too early. Except during finals, don't they open late?
Like maybe an hour or two later, but it's not like.
That's not enough. Yeah. Well, let me say one more thing about driving force. So driving force for Lewis, we don't have to worry about, but the driving force for other reactions we do have to worry about. And the way I have it organized is I have it organized by driving force. So, for example, if you have a single replacement reaction and you have gas formation or precipitation, is that a driving force for a single replacement? No, no. It's only driving force for metathesis, so we have to watch out for that. But there is one other thing. I need to talk about. Let me talk about that before we get to this. And then there was in chapter 6. This thing. What are all the methods for redox that we have? We had the element plus element, combination, or decomposition. Decomposition would be the reverse. So an element plus element, like 2 hydrogens plus an oxygen, yields 2 waters. The forward direction would be the combination. The reverse direction would be the decomposition. I don't like combination decomposition as a category of reaction because you could have redox combination, this is redox, or you could have acid-base combination, or you could have metathesis combination, and they all have a different driving force. So if this is a redox combination, then we use redox driving force. What is the redox driving force? Stronger oxidizer to weaker oxidizer. So the oxidizer here is O2. The oxidizer on the product side is H2O. So what's a better oxidizer? Oxygen. And stronger reducer, the reducer here is hydrogen on the left. What's the reducer on the right? H2O. And so hydrogen's better. And so we're going from stronger to weaker. Whereas in metathesis, gas formation is the driving force. Let's look at the decomposition. The decomposition is the reverse of this. So if I just rewrote this back, starting with water and decomposing this into 2 hydrogen gas plus oxygen gas, is this a driving force? Because we're forming lots of gas. No. And so why does gas formation and precipitation work in metathesis and acid-base reactions, but it does not work in redox? And have you thought of that? And so these are the things you think about. Like, first you memorize it. First you got to memorize the driving forces. And then after a while you get to thinking, why is that? Why can't I use gas formation? Why can't I use precipitation? Well, gas formation does help. You know, so if you have gas formation and you have precipitation, that helps the driving force. But you can't use that as a primary driving force for redox. Why?
Isn't it because we're doing the opposite? We're going from something weaker to something stronger again. So even though we are having gas form, it might not be enough for it to.
Well, this is a lot of gas. This is 3 moles of gas. But essentially it's that. In metathesis and acid-base, nothing changes with the oxidation state. So if you have sodium ion on the left, what are you going to have on the right? Sodium ion. If you have carbonate ion on the left, what are you going to have on the right? Carbonate. And the same thing with acid base. Nothing happens with the oxidation states. The oxidation states stay the same. And so what you're looking for are little things like precipitation or gas formation. Those little things are going to drive the reaction. But in redox, it's a much bigger thing. So for example, if you have sodium ion on the left and sodium metal on the right, those are like our Chem 4 book says, Dr. Jekyll and Mr. Hyde. Those are totally different in terms of energy. Sodium metal is totally high energy. Sodium ion is totally low energy. Over here, it's sodium ion going to sodium ion. There's no change. And so you're looking at little changes like the ionic bonds, whatever else. Here, there's a big change in the chemical reactivity of these. And so this is why in redox you can't use those little things like gas formation and precipitation. You have to use the big things like stronger. And then those big things don't change in metathesis because metathesis is just swapping the ions. That's it. The ions are still there. So we have element plus element. We have single replacement. What else?
Combustion.
We have combustion. Actually, let's put combustion up here. And
Skeleton.
skeleton. Before skeleton, I talked about chart and then skeleton. So if you have these down, mastered, then what if I threw out a hybrid? You know, a hybrid problem. Then you're much, if you have these mastered, then it's much easier to get like a much more difficult problem. And so let's do like a hybrid problem here.
Also, like if it was none of those, then it would be a hybrid.
Yeah,
Got it.
well, it's a combination,
Yeah.
these. So this hybrid problem I'm going to do is I'm going to take some C22, wait, no, C12, H22O11, solid. This is sucrose or table sugar. So we'll take some sucrose, we're going to add some potassium dichromate. What's the formula for potassium dichromate?
K2CR2O7.
CR2O7. Aqueous and hydrochloric acid, HCl. So sucrose this is soluble in water. So the first thing is if I take some table sugar and mix it with potassium dichromate, aqueous, and HCl aqueous, that sugar is going to dissolve. And so I might have started with solid sucrose, but in this reaction, it dissolves. So I have C12H22O11 plus potassium dichromate plus HCl. And then people look at this and they go, okay, it doesn't quite fit any of these, or it doesn't appear to fit any of these. And so you start looking, you start, well, here, this looks like double replacement. So if I do K2CR2O7 plus 2 HCl's, I can make H2CR2O7 plus 2 KCl's. And so here I have a double replacement. This is a stronger acid, this is a weaker acid here. And so I have a double replacement, I have a driving force for this. And so I'm going to form, do you know the name of this acid? This dichromate is going to form dichromic acid. So we're going to form dichromic acid. But do you think this is the major? Well, it depends. Then we start thinking about chemical properties. Can you tell me the chemical properties of HCl? If I gave you that as a test question, would that be easy points for you or would that be difficult? For me, it'd be easy points because we covered the chemical properties of HCl. I wrote them all on the board a long time ago. Do you have them memorized? Okay, if you don't have them memorized, can you tell me? Let's derive them. What are the chemical properties of HCl?
Strong acid.
It's a strong acid, yeah. What basis does it react with? not all bases in the universe it won't react with.
Stronger
All Bronsted bases.
It'll react with all bases, stronger or weaker than water? What do you think?
It doesn't react with all metals.
Stronger?
Well, that's a redox.
Question mark.
Yeah, well, you're right. That's good. Go with that. It reacts with all bases stronger than water. Any base that's weaker than water it won't react with. Right? The leveling effect. Okay, what else?
Does it just mix it?
Well, it reacts with a lot of metals, but not only metals. Will it react with gold?
Doesn't it react
Does it
with
react
active
with
metals?
copper? No. What metals does it react with?
Active metals?
Zinc.
The active metals, it reacts, yeah.
Certain, not all.
Yeah, that's good. If you remember the active metals, that's good. It does react with active metals. Is that it, though? Will it react with species that are non-metals?
What about metalloids?
Okay. So it's going to take you some time to figure it out, but if it takes you time to figure this out, how much time do you have for the hard stuff? Because this is the easy stuff. This is stuff we covered in class. This is the stuff I already gave you the answer for. And if you spend that much time on this particular problem, you're going to be screwed. That's why I changed how I studied. So this is what if somebody asked me the chemical properties of HCl and the instructor already went through it, I had it down. That was easy points. Easy points. Then I can spend all my time trying to figure out hybrid stuff like this. It's just one step more, you know. When a lot of people I've given this problem on test. I'd say only about in a class, maybe about 3 people got it. Why? And so a particular problem like this, we think about the chemical properties. And HCl, okay, HCl is, in terms, yeah, it has metathesis properties like this. It has some redox properties, metals and that kind of stuff. And so what we say is, yeah, HCl has some metathesis, has some redox, has some acid-base properties. What about potassium dichromate? When you think about potassium dichromate, does something stand out in potassium dichromate? What stands out? Well, nothing stands out with potassium ions. You know, so what we do is we can inventory everything. So as far as inventory goes, we're going to have sugar molecules. We're going to have potassium ions. We're going to have dichromate ions. We're going to have H+ and Cl-. We treat these one at a time. Cl-, the metathesis properties are silver ion, lead 2, and mercury 1 precipitate. H+, any basic anion, stronger than water. Acid-base properties, chloride is pretty much worthless as a base. It's so bad we call it neutral. H+ will react with any base stronger than water. Redox properties, chloride is a reducing agent, but it's pretty poor. It's really hard to oxidize chloride. H+ is a moderate oxidizer. How about dichromate?
Strong oxidizer.
Strong oxidizer. How did you know it was a strong oxidizer? Come on.
The 2 chromiums are at +6.
Yeah. The 2 chromiums are +6. Or, if you look at that chart over there, you know, fluorine's at the bottom right. Dichromate is, okay, fluorine's number 1, hydrogen peroxide number 2, permanganate number 3, chlorine number 4, dichromate's number 5, I guess. Is that right? Number 5? Yeah. And so it would be the 5th most powerful oxidizer on that chart. And so that's the other way you would have known it, you know, because +6 may or may not. You know, we had sulfate, but was sulfate a powerful oxidizer even though that was +6? No. And so we know dichromate with acid is a powerful oxidizer. Potassium ions are the second worst oxidizer on the chart. or actually on our chart it's the second worst. It's the third worst oxidizer on that chart up there. Lithium ion is the worst, followed by rubidium, followed by potassium. On our chart, potassium is number 2. And so this is really poor. Water is even better than potassium ion. And water is not really thought of as much of an oxidizer or a reducer, for that matter. What about sucrose? So I assume most people have some experience with sugar. Would you say sugar, as far as redox property goes, there's no metathesis, right? And there's no acid base for sugar, unless it's Lewis. There could be a Lewis, but Lewis is, we aren't going to worry too much about Lewis. And so no metathesis, no acid base, that leaves only redox left. And so if we think of sugar, is it electron rich, electron poor, or just kind of happy as is? And then we think about oxidizers, like the prototypical oxidizer is oxygen, and the prototypical reducer is hydrogen. And we know that hydrogen is extremely flammable in the presence of oxygen, so reducers are fuels. Can you burn sugar? Yeah, you can burn sugar. We can burn sugar, no problem.
I thought it just caramelizes.
Yeah, it caramelizes it, but what if you burn it to black carbon deposits? Like in your pot, you'll have charcoal-like deposits. Well, what some people do is they burn those off too. And so they just leave them on the stove until the black deposits burn off. And that's, so what we could have is partial oxidation. That is, we could try to caramelize it, but some people overdo it and burn it. And so we could have partial oxidation, which makes carbon deposits. And we can try to oxidize it a little bit further to make carbon monoxide gas, and then oxidize it even further to make carbon dioxide gas. Can we go beyond this? No. And so this is called complete oxidation. So we might have partial oxidation. When we caramelize it, we just want something in here. Your body can burn it too. Oxygen is the prototypical oxidizer, so the symbol for oxidation is this. In your body, if you eat sugar and you inhale oxygen, eventually, do you know what your body will do? It'll metabolize it completely to extract as much energy out of that, and then what's left of the sugar is just CO2. You just exhale the CO2. So this would be complete metabolism of sugar here. And so your body and the flame kind of do the same thing, except the products here are different, that you get. Doing it in the flame versus doing it in your body. But overall, the net reaction is the same. We're going to completely oxidize it to CO2. And so you would say that even though sucrose is not on the chart, you would say that this is probably a reducing agent. Yeah? Okay, so which of these reducing agents is easiest to burn, to combust? Would you say sugar? Let's say you ran out of sugar, and what are your choices? You can try to burn chloride or water. Are these easy to combust, chloride and water? No, and so the strongest reducing agent is going to be sugar, and the strongest oxidizing agent will be dichromate in H+. Now, how do I know dichromate in H+? Because it's on the chart. Dichromate, Cr2O7, 2-, is going to require how many H pluses? There's 7 oxygens, so how many H pluses do I need? 14 H pluses. And then we're going to take this all the way to chromium-3. That's what's on the chart, chromium-3 ion. So we're going to go from +6 to +3. And so +6, and we have 2 of those, so we'll need 6 electrons for that. And this is going to make 7 waters. Okay, and so that's exactly what's on the chart. If we go number 5, dichromate plus 14H plus 6 electrons yields 7 waters plus 2 chromium 3 plus. It's just written backwards from the chart. So this is from the chart. Okay, so now what I did was I made this problem a lot harder because is sucrose on our chart? No, sucrose is not on our chart. And the problem is skeleton redox is supposed to tell us the major product, but we don't have the major product here. How can I balance it without the major product? I can't. And so what I have to do is I have to assume something. Either I just leave it alone or I try to assume, what do you think the major product will be for the oxidation of sucrose? Well, it could be anything. You know, it could be a whole bunch of these things. But, you know, to keep it simple, we're just going to assume that it's going to completely oxidize. And that is when we burn sugar, we're just going to assume it forms CO2 and water. It might not. It might form soot, caramelized sugar, carbon monoxide. But, you know, there's too many things, so we'll just assume that it goes all the way to CO2. So this is a critical step here. A lot of people won't get this step because they don't know what to write here. And so we have 12 carbons on the left and we have 1 carbon on the right, and so we'll just put 12 here in front of the CO2. That will give us 12 carbons. And then we have 22 hydrogens on the left and no hydrogens on the right, so we'll just do plus 22H+. And then we have 11 oxygens on the left and 24 oxygens on the right. And so I'll need 13 waters on the left. And then we have, oh, did I screw this up? Yeah, oops, I screwed this up, sorry. I screwed this up because I don't do hydrogen first, I do oxygen first. And so let me redo that. I have 11 oxygens on the left and 24 oxygens on the right. And so I'll need 13 waters. And then I'll do the hydrogens next. 22 plus 26 is 48 hydrogens on the left and no hydrogens on the right. So I'll do plus 48H+. And then the charge. 0 and 0, and then plus 48. So I'll need 48 electrons. And so what we end up with is this. We end up with C12H22O11 plus 13H2O. This is going to produce 12 CO2 plus 48H plus 48 electrons. Is 48 electrons a lot of electrons? Yes. 1 mole of sucrose yields 48 moles of electrons. 48 moles of electrons, that's a lot of electrons. That means you would call sucrose electron rich or electron poor. Or electron rich. But when you look at the oxidation states, let's take a look at the oxidation states here. Which one goes first? Carbon, hydrogen, or oxygen?
Hydrogen.
Hydrogen at +1. Oxygen would be next at -2, and that leaves hydrogen at what? So this is plus 22 minus 22 is 0, so carbon must be 0. When you see carbon at 0, do you think electron rich? No. But it turns out, yes, it is electron rich. Each carbon can lose 4 electrons, and we have 12 of them. 12 times 4 is 48. 48 electrons it could lose. And so it turns out that sucrose is pretty electron rich. It's a good fuel. And so this is the other half reaction. Once we have this half reaction, then we'll multiply this one by 8. And that'll give us 48 electrons here. And so combining these two half reactions, we end up with 8 dichromates plus 96H plus 48 electrons plus sucrose plus 13H2O. This is going to produce 8 chromium, no, I screwed up the chromiums here. This is 2 chromiums. 16 chromiums, 3 plus, 16 chromium 3 plus 8 times 7, 50, 54, is that? What is it? 8 times 7, 56, that's right. Plus 56 waters. Plus 12 CO2, plus 48 H plus 48 electrons. So 48 electrons cancel 48 electrons. And I have 48 H plus. So I'm going to get 48 plus 48. I'm going to get 48 H pluses over here, I think. Is that right?
Yeah.
And then 13 waters. This is going to be 43 waters here. Oh, shoot. So overall, I have 8 dichromates plus 48 H plus plus sucrose yields 16 chromium 3 plus 43 H2O liquids plus 12 CO2. So I didn't want to erase that, but okay, then I look for driving force. So dichromate and H plus, this is our oxidizing agent. Sucrose was our reducing agent. And then we look at the conjugates. So the conjugate of dichromate is chromium 3 in water. The chromium 3 in water must be our conjugate reducing agent. So the chromium 3 in water, this is our reducing agent. And the conjugate over here is CO2 and H plus, but we only have CO2, so this will be the conjugate oxidizer. Here. All right, then we look. What do you think is a better oxidizer, dichromate or carbon dioxide? Dichromate. Do we even need the chart for that? Because it's not on the chart. No. For sure, dichromate is going to be way stronger than carbon dioxide. And so this is our driving force. Here. If that's the case, then sugar is a lot easier to burn than chromium 3 ions in water. And so that makes sense as well. So this is a hybrid in which you're going to need some additional knowledge, you know, for sugars and burning, this kind of stuff. Dichromate is a better oxidizer than oxygen. What is oxygen's rank? Dichromate's number 5 on that chart. Oxygen is number 6. Oxygen has no problem burning sugar to CO2. So you'd expect dichromate would have no problem burning sugar to CO2 either, under the right conditions. Was there a specific problem on the test, or do you want to just do all of them for review? The very last one? All right, let's take a look at the very last one first.
Because I think I psyched myself out when I saw the word alloy, and I just
Yeah,
stopped.
you know, I regret not having you do chapter 4 homework now.
I just
But I did something similar to this. And when we have a mixture like this, my preference is not to do system of equations. It's like 2 equations. My preference is to do the chart method. But I shouldn't call it the chart method because I'm using chart method for the other one. Let's call it the graphical method.
So So did a lot of people not get this one, right?
I didn't even, I wasn't even able, no, I wrote something down.
A lot of people got this one, actually.
I'm glad
Alright.
they did.
Yeah. A lot of people got this one.
Wait, but how is the average so low still?
Because it's
And the-
confusing.
No, but like,
Multiple choice seemed to.
Yeah, it was the
Um,
little things that killed me on that one.
yeah, cause I was able to at least get a solution for 38, but 39, I tried and I just couldn't finish it.
All right. So what we want is we want the percent magnesium, but we don't know what it is, or the percent aluminum. So there are two unknowns here for this. And in this particular problem, what we do is I like to use the graphical method because visually we can see it. If I have 0.27 grams of magnesium and aluminum, like this, it turns out that they yield different amounts of hydrogen. So we could do a quick calculation. This is a common in multiple choice questions. Which one yields more hydrogen per gram? A gram of aluminum or a gram of magnesium? Which one will give you more hydrogen? Well, we could do a quick calculation for this. 2 moles of aluminum weigh how much? Well, aluminum weighs around 27. So 2 moles of aluminum would be 54 grams of aluminum. 54 grams of aluminum is going to produce 3 moles of hydrogen. 3 moles of hydrogen is going to weigh how much? So a mole of hydrogen weighs 2 grams. So 3 moles of that would weigh 6 grams. So 54 grams of aluminum produces 6 grams of hydrogen versus 1 mole of magnesium. If we look at 1 mole of magnesium here, magnesium is going to weigh 24 grams. And so 24 grams of magnesium is going to produce, well, H2 is about 2 grams per mole, 2.02, 2.016. So that's going to be about 2 grams of hydrogen. So which one yields more hydrogen? Well, what I like to do is I kind of like to normalize it. And so if I multiply this one by 2, roughly, by 2, or I multiply it so that it equals 54. Suppose I could do that. Then I get a 48. So if I have 48 grams of magnesium, this is going to produce 4 grams of hydrogen. If I multiply by 3, that's going to be 72. 72 grams, this would be times 2. This is times 3. 72 grams of magnesium will yield 6 grams of hydrogen. So which one yields more hydrogen? Aluminum. Do you see that? Yeah, in order to produce 6 grams of hydrogen, I need 54 grams of aluminum versus, in order to produce 6 grams of hydrogen here, I'd need 72 grams of magnesium. And so aluminum yields more hydrogen. And so this gives us a way to determine how much aluminum and how much magnesium we have. So if this were 100%, then this is the way we do this. I assume it's 100% aluminum. If this were 100% aluminum, then we say all 0.275 grams are aluminum. So we go 0.275 grams of aluminum, and then convert it to moles, and we're going to figure out how much hydrogen is produced. And so it's 26.98.
Why would we assume it's all aluminum if it's an aluminum magnesium alloy?
Why? Because we want to see how much. If this were pure aluminum, then we're going to get the maximum amount of hydrogen we can have. We can't go beyond that. And so grams of aluminum per mole of aluminum. Oops. this is upside down. 1 mole of aluminum per 26.98 grams? Yeah, 26.98 grams of aluminum. The grams of aluminum cancel, that gives me moles of aluminum. And then the mole ratio there's 3 moles of hydrogen for every 2 moles of aluminum. And then the molar mass of hydrogen, which is 2.016 grams of hydrogen, H2 per mole of hydrogen.
What did you do over there? I get the times 2, 24 grams. You get 48 and then 4, but how'd you get the 72?
As it times 20.
Oh, I said 24 times 3.
Oh.
That's where that came from. This is going to be the max amount of hydrogen I can produce, 0.275 divided by 26.98. We don't have to, this is optional. You don't have to do this.
You can just-
But sometimes there are multiple choice questions asking this, especially on standardized tests. I've seen that question a lot on standardized tests. We would end up with 0.0308 grams. Let me do one more digit. 0.0308 sub 2 grams of hydrogen. Could this be pure aluminum? We would have ended up with 308, but we only ended up with 249. Could it be pure aluminum? No, it can't, because we didn't produce. Could it be pure magnesium? And so next we're going to assume 100% magnesium. And so the whole sample, 0.275 grams, will be magnesium. 1 mole of magnesium per 24.31, we'll just say, or 24.305. And repeat the same calculation. 1 mole of hydrogen, 1 mole of magnesium, 2.016 grams of hydrogen per mole of hydrogen. Okay, check that. Go ahead and do that calculation. We'll just have to take. Okay, unfortunately we're out of time, so But how many grams did you get for this?
0.228
0.00228 sub 1 grams of hydrogen. Could this be pure magnesium? No, so it's in between pure magnesium and pure aluminum. So 228 is pure, 308, we're at 249. And so it's closer to, so 100% magnesium, so there's going to be more magnesium than there is aluminum. Do you see that? And so what I like to do is I like to graph it and come up with an equation. Do you remember doing something like this, similar? And so this is called the graphical method for, it works nicely if you only have two components and they yield different amounts of hydrogen. If these things yielded the same amount of hydrogen, it won't work. But they yield different amounts of hydrogen. Anyway, we'll finish this later.
Do you have office hours today? Or?
No, I don't. I have to go. I have an appointment, and so this was part of the appointment to deal with. But